So, I am duty bound by the state of California to ask you both if I have the permission to record this video.
Absolutely.
Goodbye, me.
So we have Matt Andrews and Dr. Adams, again, returning guests to this particular video recording, talking about what they're working on currently. And we had the opportunity to kind of convey possibilities before we started the conversation. So, Dr. Adams, as you're up, having finished your graphing and whatever you needed to do prior to actually getting on this recording, you were going to talk to us about the new A-Life conference that's coming up.
Yes, that's right. That's been my main project.
So, how's it looking?
Oh, yeah. So, yeah, I can just dive right into it. That sounds good. Everything is looking great. We're really excited. This is going to be a really big year for artificial life, just generally, because it coincides with so many different things that are really cool and A-Life-y, including the new A-Life Institute. So yeah, everything is just going super smoothly. We have a lot of amazing people on the team who are doing an incredible job. We have a really large planning committee, which I really enjoy because I love working with people and getting to know people that way, which has been a lot of fun. But yeah, the calls for special sessions, workshops, and tutorials just went out, and the deadline is the last week of February. And we also have the calls for papers going out as well. So be on the lookout for that. But you can go to the website and you can see all of these amazing deadlines and more information at 2025.alife.org. That's 2025.alife.org. Super easy to type in. So I encourage everybody to check it out and to follow along on the socials. We have Blue Sky. I don't think we have Twitter, but I think we also have a TikTok, actually, because we plan on making a lot of videos, especially with Amy.
Me claim to be doing the videos, actually. I've been waiting for him to get in contact with me to actually get my videos so he can start doing the TikToking of them. But for folks listening in, the Institute, this is news, obviously. Can you talk a little bit about it?
Yeah, so I can talk a little bit about it because it was announced last year at last year's A-Life conference in Copenhagen. And right now, we are doing a lot of things behind the scenes at the Institute, and we are going to make an appearance, and we're going to share a lot more information at the conference about, what's happening, what's the Institute about, how can people get involved. Unfortunately, I can't share any more details than that because it's all very secretive and going in the background, and things are changing really quickly as we build and grow and develop. So you'll have to stay tuned and check it out at the A-Life conference to learn more.
Very good indeed. So for folks listening in, for folks watching more importantly, what kind of research, what kind of things would be worth submitting to the A-Life conference? This has always been a sticky topic in this particular video recording, but what kind of stuff are you looking for?
Anything that has to do with artificial life. And we're going even broader this time because it's not just about science, right? Because there's a lot of amazing models and research and really exciting things. But we also are bringing in people from industry and companies and people who are hobbyists and artists and writers. So there's going to be an opportunity for everybody who's interested in artificial life in some sort of way, right? So literally anything. I don't know, if you even just want to show up and you just want to come to the conference to learn more, you can do that as well. There's a huge community that's really welcoming, and there's going to be a lot of opportunities to learn more about what A-Life is and how you can get involved and get involved in research. And how can you turn some of these really amazing ideas that come from research into products and toys that everybody could use? Yeah, very, very broad.
So the political question, will Bitcoin papers be allowed?
I think that we probably don't want people promoting meme coins. However, cryptocurrency and blockchain is an absolutely fascinating question. So I think that, of course, we welcome research that has to do with Bitcoin and blockchain and crypto in general, but we're gonna step away from shilling meme coins. So, so yeah.
Very good. Matt, any questions?
No, not really. I was guess the only thing I'd be really curious about is I'm working on trying to get a paper together myself, and I think this year's conference goal aligns really well with what I'm doing, and so I'm just trying to wait out until the submission criteria comes out so I can see what kind of a bar I need to be hitting. I've never done anything like this before, so it's going to be an experience.
Awesome. And then we're also going to have like submission guidelines for things that are just like, for example, maybe you have like a really cool simulation that just looks awesome and it's art, but it's maybe not like an expo or something like that, but you want to show it anyway. There's also going to be opportunity for things like that. So like so our dream, I'll share this. Like one of the dreams that we want to have is we want to have these screens around the venue where people's artwork will pop up or their models, right? So like you can have some simulation, a life world going and you can look at it and it's happening in every room. So we were thinking about them as like aquariums, right? So there'll be space for that.
That's a really neat idea.
Be fun.
One of my earliest experiences was actually doing that for nightclubs in Australia when I first started developing simulations. There's like literally XT machines, AT machines with the screens doing, brain simulations and various other things. So yeah, the artwork part. Is Vida still connected with the A-Life conference, or is Vida doing its own thing? I remember there was some intertwining of Vida and some breakaway. Are you familiar with Vida? It's I think it's a Spanish language A-Life Art Prize, which is an annual prize.
Oh, right. I'm honestly not sure. I should check into that and see if there's any involvement this year. Stay tuned, I suppose.
There's usually attendance of Vida-related people, which is when I've met my Vida people, but I'd already talked to them previously. So it was actually quite cool to go to whatever was the one in 2012 and, have meals with the various Vida folk and talk to them about how just amazing the field of artificial life art really is.
Mm-hmm. Yeah, beautiful. I mean, like the things that come out of people's A-Life worlds are completely amazing and beautiful and unexpected. And I think that just deserves like a lot of recognition and space, just to appreciate the beauty of these worlds that people are building.
So in terms of your own work, in terms of the trajectory, I've met Olaf. Olaf is going to appear in an upcoming recording. A hard man to track down and keep it times with regards to particular conversations. He has a conversation with Charles Offria of maybe 10 years ago that Charles had told him that if he ever met me that he needs to have this conversation. I thought that's a perfect podcast right there. So in terms of your plans, what's the world of A-Life looking for Dr. Adams like?
So I'm coming from a background, well, at first I came from physics, right? But then I studied open-ended evolution and continued it a little bit. But I think that what's interesting for me is a lot of those conversations really sort of like, they didn't crystallize, but they sort of ended up in this place of, it turns out you can make open-ended systems and we're just understanding it incorrectly because it has a lot to do with how we subjectively experience and judge the things that come out of it. So because of that, I started to think a little bit about like, well, why did I get into open-endedness in the first place? Well, it's because I was really fascinated with origin of life and how biological evolution is constantly making things that have function and purpose. For example, of course, everybody knows about the genetic code. That I think is a really amazing structure that has a very, very specific function. But before that, like even simpler, I don't know if it's like before. I guess, yeah, before that, like evolutionarily, I suppose, there's things like proteins, which are, again, structures that have a particular shape that end up interacting with things, and those interactions cause functions between different parts of the system. So what I'm really interested in is how these structures get used as tools. So really trying to think about how these structures are come about, but not just how they randomly come about, but how they're kept in a system. I mean, sure, you can get a bunch of proteins that are randomly made, but some of them are kept because they provide some sort of purpose or function or things like that. And that starts to get into a lot of like hairy concepts that are coming together. So I've been spending the last couple of years trying to understand how these concepts interact with each other and how they are expressed in different fields, what is known, and that way we can start with a fresh, clean slate and say, this is what we don't understand about evolution, and this is what we think would be an interesting question. So a lot of it's conceptual, but I'm turning back to cellular automata and other dynamical models to make some tests and do some experiments. So that'll be my upcoming year.
Terrific. Does that involve artificial chemistry at all? Because I know certainly in terms of Dr. Bruce Damer and talking about his origins of life research, the artificial chemistry component to it was a large part. You mentioned proteins. I'm assuming artificial chemistry is in there too.
Absolutely. Yeah, exactly. And that's what's really difficult for me is because a lot of different fields that I don't know anything about artificial chemistry. So I had to ask a lot of people, and I have to have a lot of meetings and interviews with people to be like, why is this concept important in this field, and how can I understand the overlaps between what people are looking at over here? So yeah, artificial chemistry. Let's see what else. Like design, human principles of design, which is really fascinating. Another one that's really, well, obviously like thermodynamics and epsilon machines. All those are related. And yeah, so I'm putting together a big review paper to sort of showcase everything that I've learned. it'll be
Certainly,
yeah.
Certainly artificial chemistry lends itself very heavily to cellular automata. I mean, a lot of stuff builds out of that, particularly with carbon-like chemistry simulation. So it's fascinating how it all kind of comes together. Matt, do you have any questions?
I really like the fact that you brought up proteins and discussing about how they are come about and they go forward in time, because that's really relevant to the kinds of things that I'm working on with my mutable encoding genetic algorithm. So I think that if you later on when I'm talking about my stuff, if you have anything to add to it, feel free to jump in or ask questions and fire away. But I really find that interesting.
Yeah, it's super fun. And I'm really excited to use cellular automata again to answer these questions. Like, so there's this video on YouTube that's like game of life in game of life. I think if you just Google that or put that in the search bar on YouTube, it'll pop up. But basically what it is you have like this regular cellular automata, but you get these like gliders and they're sort of like interacting with each other. But there's these persistent structures in the way that the game of life is evolving. But when you zoom out and you look at it and you keep zooming out and you keep zooming out, it turns out these persistent structures and these gliders that are going back and forth are actually making a simulation of the game of life rules, but on a macro scale. So when you zoom out, that's what you can see. So when I'm thinking about like these things like proteins, I'm thinking of these persistent structures that if you look at the system in a slightly different way, might look like it's evolving under dynamics that are not random, but are looking like they have some sort of like rules or something, or like another kind of rule. So yeah, I don't know. I'm super excited. I like to think about it all the time, but I gotta have some results first.
Does the simulation produce the results, or do the results need to exist first?
For the video?
You're looking to produce results first, you said, before you get into the actual simulation part. And I was wondering, it seemed to be cart before horse, but I wasn't sure.
Oh, right, yeah. No. Like, because what I wanted to do was I wanted to look at some cellular automata, trajectories, and I wanted to coarse grain them in a different way, such that you can say, like, if I coarse grain it in this way, does it look like another rule? Now, this has already been done before, but I think that what I would introduce differently is I would try to pay particular attention to the relationship between the coarse grained result and any static structures that are still existing within the cellular automata. So I feel like in order for me to say something like actually useful about this relationship between persistent structures and a way you would describe a system according to a particular rule or something like that, I'd like to have some results, but first I need to finish my grout, move to Japan, and of course, like, take care of the A-Life conference.
Very good, very good. Dr. Adams, anything else you'd like to pass on to the users before we move on to Matt's update?
No, I don't think I have anything else right now. You know, of course, there's always a lot of events going on at Crosslabs, which are really fun. So if you're not on our mailing list, please join us. Otherwise, you can check out our socials. We have another workshop coming up in a month at the beginning of March, but which, by the way, is a hackathon. In case you are both interested, we want to have a week-long project share and collaboration where we talk about how we can use technology to interface with reality in different ways. So, like, can we augment our senses? Can we, like, understand reality and experience reality in new ways? So that's really cool. And for anybody who's listening, you can go to the Crosslabs website and check it out. It's called New Human Interfaces, and that's in a month. So if you want to join, please email me at Alyssa at crosslabs.org.
Is Python a requirement, or is any language acceptable?
You can use whatever language. You don't even have to know how to do computer programming. You can just show up and share your ideas, and maybe somebody else in your group will know programming and can work with you.
Very good, very good. Matthew, you have the floor.
Alrighty. So I'm going to just take a quick second to give a short brief on kind of what Mega is. So Mega is a different approach to genetic algorithms. It uses a set of default genes called delimiters, and they arise into the chromosomes through mutation as we go through the different various generations and breedings. And what they serve is as demarkers of sections of genes, and it regulates the mutation rate inside of the delimited area. And then there's another mutation called a capture mutation, or a captured metagene mutation. And what that does is it takes genes that are between the delimiters and captures them as a single unit and assigns a new encoding to them. And so by virtue of their existence in the solution space, they create new genes that can be used to generate further solutions. So it creates metagenes, which can be nested together to create a hierarchy of, I guess you could say, evolved abstractions. And then each one of those metagenes can be reopened, unpacked, and subjected to mutation again to allow for updating forward as it progresses through. And what you end up with is kind of a network of genes that build a hierarchy of solutions, modular solutions that could be reused in creating and evolving new solutions going forward. So it's kind of like two genetic algorithms on top of each other, one that's evolving the gene set and the other one that's actually evolving the solutions. And since metagenes are created through the entire population, from the best to the worst solutions, what you wind up with is kind of a global effort towards building this metagenome. And I was testing out or messing around with a concept of treating the population or the entire genetic algorithm actually as kind of like its own organism, since it's kind of a global process. And all of the organisms have access to the same higher level hierarchy of genes in the network. And so I was testing it out in what I'm calling, actually, I don't really have a name for it, but it's kind of a spatial search space, I guess you could say, where the things that are being optimized for are represented as 3D space. And the genetic algorithm evolves a path through that space as a way of interacting with what it's trying to construct. So I guess you can think of it as like a workbench, where the algorithm reaches out, picks up a piece, and can manipulate it inside of this environment. And the fitness function is applied to the space itself. So whatever we're optimizing for, you measure against the entire population. So each evaluation makes a change or an update to the space, and it gets a score based on the state of the space against what we're targeting for. And one of the applications I thought of this was being able to apply it to spatially embedded neural network, where the network itself is defined by the interaction of the other neurons in the space. So one of the ways that I did this was taking a neuron and defining its connections into other neurons as a sphere around it, like a sphere of influence. So if two neurons are inside of or if one neuron's inside of another neuron's sphere of influence, then that neuron can connect to it, which if you play that out with a variety of randomly initialized neurons with each with their own sphere of influence, what you wind up with is a network that wires itself up based on proximity. And then from there, we derive the weights and biases of the network based off of how far apart neurons are for the strength of the signal. And then the connectivity of a neuron, what it's receiving from other neurons, is how I go about deriving the weights and biases for the networks. And so it's just kind of a way of spatially embedding a neural network inside of a three-dimensional space that can be acted on inside of that workbench, where the algorithm can act on it to manipulate and design the network. Right now, I am mainly focused on getting the network wired up, and what I found is that the best way to go about it is have the network with a density that's high enough where it's 100% connected, and then allow the algorithm to shape how it's arranged inside of the space. And then once I'm satisfied with the results that come out of that, I want to move on to actually turning the network on and trying to get it to a state where it's self-regulating. And so the idea behind that is I am going to have I guess you could say, a variable that I consider called the activation bank is what it is. And that's going to be fed into one of the nodes, the value of the activation bank. And then the fitness function there is going to be based off of how many activations the network sees are being deducted from the activation bank. So the network has a sense of what its activation levels are, and then feeding that back into the genetic algorithm as the fitness score. And then what I'm going to do is I'm going to activate the rest of the remaining neurons, or input neurons, with random signals, random firing. And I'm hoping that what's going to happen is that the mega algorithm is going to arrange the network in a way that can optimize for the target number of activations. Now, each neuron also is self-updating in that it's similar to Hebbian learning, where the more it activates, the wider its connection radius becomes. So as it increases its activation, it basically widens the sphere of influence, and so it can create new connections on the fly, or through inactivity, it shrinks down the radius, so it becomes less connective to other things. So you can imagine a network that is adjusting itself based on its functioning. So if you have an overly active neuron, it's going to continue to expand until it touches all the neurons. But with the genetic algorithm working to optimize the network, if we're trying to minimize activations to like prevent like cyclic behavior where it's just cycling a signal back and forth and activating the certain neurons over and over. That's going to give it negative feedback. So it's going to tend to arrange the network in a way to avoid that. And so we're talking about something that can, through feedback, sense its own state if it's overactive or underactive and modulate from there. And that is the initial setup that I'm using to essentially train the neural network, or train the network to self-regulate, be a way to put it, in conjunction with genetic algorithms. So we're treating those like a single thing, where the genetic algorithm shapes the neural network, which changes how the network activates and gives feedback into the genetic algorithm. And then you combine that with the activation bank, and you have a way of having self-organizing in a sense of how much activation it can tolerate versus what it's receiving back, because we're going to have a reward function in there also too. So as it performs well, we're going to increase the activation bank according to the reward. So it has, I guess you could say, almost like a drive to bank activations for later use and self-regulate. And then once we get to a point where we can understand, or I can get the network to understand that that is a reward and it can self-regulate against random inputs, which, I mean, random inputs are just going to be an array of activations, just noise to it. And so if it can self-regulate through through the random noise to stay within the constraints, that's when I'm going to consider that a pass for understanding what reward is. And I'm going to move from there to phase 3, where we actually start training for a specific target behavior. Maybe we provide it with meaningful input, like a state of the screen or something like that, and start off with something simple like a really low resolution cat and mouse game where, you know, the agent's expected to move in the direction of a mouse that has its own path that it's following, and see if I can get some kind of anticipatory behavior out of it. Like, it knows that learning the physics of the rules of the system, and I'd consider that positive. So we continue to, with the reward of increasing activations, and see if we can get just kind of an online adaptive behavior out of it. So that's just the kind of overall concept of what I'm working with right now. And one of the things that I think is interesting from what I'm seeing, and I have a, I guess you could say, a little mini example of where I'm at right now, and I'm ready to go and show on the screen. But I guess what I'm looking for is a means of online learning for a neural network. And this is what I think is, at least as far as I know, a completely new approach to training neural networks, because I've read about spatial embedded neural networks before, but I believe what they did is they had a regular neural network, and then they assigned spatial encoding or spatial representations to the network, and they had like an associated cost function per activation. And they found that they got really interesting structures out of it that were similar to, I guess you say, structures that you'd see in a brain. And that was based off of just associating cost with distance as far as activations go. And this is a little bit different because the entire network is represented inside of a physical space, or a virtual physical space. And I'm really excited to play around with this, because so far the results have been really positive. It took a little tinkering to kind of figure out the mechanics of how it works, because once you throw it all together, you know, you can't always predict the behavior you're going to get out of it. And so it's interesting to kind of see how it changes over time. And once I'm satisfied with that, we're going to move to phase 2 through to phase 3 and see what we get out of the end of it. But if you are ready, I'll go ahead and share my screen and just kind of give a brief run through of it. All righty. Screen, share. So this is kind of a shrunk down example because it's actually really difficult to display all this in real time with the visualization. And what you see here is the actual network, and the green line is the GA agent going through running, and picking things up. And you can see the red triangle, that's kind of the base mark, but when it drops a neuron, you can actually see the red square move, and you can see the network reconfiguring itself as we go. It's really...
What's the red one again? What's the red triangle again?
So the red triangle represents where a neuron is dropped. So you can see here when it updates, there's a red triangle. You can see the neurons moving and rewiring as it goes. Or right here is one, and you can see it shift. And so that's essentially what it's doing, is it's relocating the neurons, and they have their sphere of influence, which dictates where their output goes. So it's not bidirectional. It's basically, if a neuron is inside of another neuron sphere, then the neuron sends an outgoing connection to it. So that's how it's all flows in one direction through the network. I'm going to go ahead and turn it off real quick and let it go, because it runs way faster when it's not being rendered live. And then we can see where it goes in a couple generations. And so the structural connectivity here is basically the percentage that it is connected from input to output nodes. I treated that like each connection reduces the number of groups by 1. And so it's basically from 100% disconnected to 100% wired. And it always shrinks down a little bit because it gets disconnected. That's why I keep the density up, because actually it has a little bit of a harder time going from low connectivity to high connectivity. And I give it the opportunity to just kind of shape the network as it goes. And so you can already see when it comes up, we're getting some more interesting structures that come out of it. And bear with me, it's a little bit hard to rotate when everything's being rendered, but you can kind of see there's more organic looking structures where you can see the higher connectivity going down to lower connectivity, and then into larger, more, I guess you could say, organic looking forms.
Oh, Tom had a question.
Yep, I'm sorry, I can't see you. What do you got, Tom?
I was wondering if the neurons were floating or whether they were actually fixed. Because if they're floating, sorry.
They're fixed.
If they're floating, then you can get interesting, almost kind of magnetic responses between them as well. So it'd be interesting to see a similar simulation where they are actually floating, and it creates a different kind of interaction, basically. But I like the idea of the sphere of influence kind of expanding on them. And I think that's what you were demonstrating. So I'll let you go back to doing what you were doing.
Right. So I think that having them kind of float on their own would be an interesting case. But the whole kind of point is to make this under the direct control of the algorithm. So if they're floating and moving on their own, it makes it a little bit harder for the GA to interact with it. Now we're only 4 generations in. It's a little bit slow because each time it relocates a neuron, it has to go through and recalculate the connectivity. And I am sure that there's faster ways of doing this. I'm not exactly the most optimizing person. Right now, I'm just trying to get the concept to work. And once I get satisfactory results, maybe I'll go back through and try and optimize it a little bit better, because this isn't developed all the way through. It's just kind of as I go. When I bump into problems, I fix them and keep moving forward.
So wait, what was meant by floating? Is that like 3D space, and then fixed was like 2D space? Is that what the question was?
No, they can still be fixed in 3D space. I mean, I think the notion of floating just means that they can move through the space in ways which you could use Brownian motion or a variety of other different ways. And that actually makes it a more interesting simulation from a movement perspective. And you can have almost like gravity relationships or electrostatic relationships between the various neurons. So I'm thinking here of Hiroki's stuff that he's doing currently, which is very similar in some regard, but they're all floating. And it creates an interesting but very different simulation to what Matt is doing. So I just wanted to ask the question.
Thanks. That makes sense. I also had a question. So I didn't fully get what the green paths are. So the red one is a new neuron that you dropped in, right? And then
it's actually the relocation of a neuron. So that is a relationship to the green path. The genetic algorithm itself has a series of what is evolving is basically the path. It's a set of moves up, down, left, right, forward, backwards. And when the path travels over a neuron, it picks it up. Now, I have this, I had to work this a little bit because I was trying to get continuous control out of it. And one of the problems is that, you know, if you're plotting a path through a space and continuous space and you're treating like path overlapping with the neuron, you have to hit it dead on in order for it to be considered pickup. And that just wasn't going to work. That's too, it's a little bit too precise of an expectation. So the path itself has its own sphere. And there's also genes that scale it up or scale it down. So it takes a discrete step at a given scale. So what we're evolving is the path, you know, the series of moves up, down, left, right that it travels through space, but it's also evolving the scale that it's moving at. So it can scale up or scale down by certain increments, and that changes the sphere around the agent that's moving through the space. And so what the green path is basically just seeing what is actually being done by the genetic algorithm. That's the path that's being evolved.
Thanks. Yeah, that makes a lot of sense. Okay. And then because I'm looking at the output on the right here, and it's saying, because yeah, I think I'm trying to wrap my head around the sense of like I guess like what fitness means here. Because I think like with when you're training like neural nets and things like that, fitness has a lot to do with like, oh, was this image really a cat? Did it get it right? Things like that.
Right. Okay, so
like, you know,
the fitness score is a little bit different because it in some ways it's almost an arbitrary value. The path itself, I have to have a fitness value for the path to say, hey, this is a good path, and the goal is for it to interact with neurons. So I score the path itself based on if it picks up neurons, if it's dropping neurons, because if it's not picking up and dropping neurons, then it's not doing what it's intended to do. So it's kind of like a reward to the genetic algorithm saying, hey, yeah, that's a good path because it picked up neurons and it dropped the neurons in a different spot. But the fitness function is also a combination of the values you're seeing here. We have the structural connectivity, the connection density, which is a different kind of value, because one of the problems that I was having is structural connectivity is just basically, is there a connection? And the connection density is a calculation of, if we over here, there's the max radius, which is the largest possible radius that a neuron can have. And so what I did to get the connection density is I treated all the neurons like they have the maximum radius, and then I asked, what is a fully connected network? How many possible connections are there if every network or every neuron was connected to every other neuron? And then I took the distribution of the radiuses from the smallest to the biggest, and I subtracted that from the total to get the basically the baseline connections. What's the highest connectivity that it is capable of? So that is basically the most densely connected that the network can be, given the a normal distribution of the range of actual radiuses. And then I take that down to 0, so we get a percentage from 0 to the maximum potential connectivity of the network. And then the combined health, there's also another metric in there, which is kind of an entropy measurement. It's basically how densely packed is the network into a specific space. When you combine all of this together, basically we're encouraging the structural connectivity, we're encouraging it to increase this connection density, and we're encouraging the neurons to be clustered together. And so that's a way of just increasing the or decreasing the frailty of it, because if we rely only on structural connectivity, where there's only one connection between each neuron. If you move one neuron, it could disconnect entire sections of the network. And so by having redundancy and increasing the connection density, we're making it less frail to disruption because there's other connections that are holding the network together. So moving one neuron isn't going to disconnect a large section of the network from the rest of the network. And back to the fitness score, that's kind of a composite score. One of the things that
Oh, sorry, Tom has another question.
Okay.
Sorry, no, I was really interested by the concept of frailty, because I think frailty is what interests me about your simulation specifically, that the ability to maybe fisher elements and see what constructs after that. Maybe I just like, sticking my finger into the petri dish and wiggling it around a little bit and then pulling it out. But it seems to me that the frailty is actually an important property that should come from maybe even fissuring these things and taking them into separate simulation petri dishes, for want of a better metaphor. So I think what's fascinating with the way that you've done it is density is good, but it's a bit like overfeeding some fish, right? You're just basically creating an environment where it's going to continue to do what you want it to do. I think the fissuring or the frailty aspect of it, I find really fascinating. Have you thought about doing frailty-based experiments where you've actually rip it apart and see what happens and perhaps stick bits back together?
Honestly, I haven't had a whole lot of time to really get in and experiment with what's going on, mainly because I don't have a lot of free time to work on the stuff. So right now, I think my main goal is to see this all the way through phase 3, where I actually attempt to train it to a specific task. But once I get some proof of concept, I'm going to come back through and start playing with these kinds of things. The concept is meant to be kind of an always on thing. I had to make some updates to Mega to allow it to delete metagenes, and that's what's over here. And it's kind of died out right now because things have kind of settled into place. But as it goes, it will spike up, and you'll see 5 or 6 deletions in the deletion basket. And what it's doing is it places the genes into the unused, and then it recycles when it creates a new metagene. So it takes the old encodings and uses it to make a new metagene, and that prevents it from just stacking metagene until I run out of memory. It's just kind of a way of holding on to that space. So unused metagenes get deleted because they're no longer practical in the current setup. And again, that's just kind of a way of allowing the network to stay always on. But I do intend on taking this apart and having the opportunity to play around with it and kind of see how it goes about reorganizing itself. I've had some other experiments based on the same kind of spatial concept, and disrupting it actually kind of improves efficiency because I guess it rearranges the different items or objects that are inside of the space, and it gives it more access to locate the different combinations. So when you just randomly disrupt the space, what I've seen is that it improves the efficiency because it has more exposure to what's actually inside of it, if that makes any sense. And this is actually kind of a different way of approaching it, because genetic algorithms themselves mainly rely on a fixed fitness function. They don't interact with a space that they can disrupt themselves because it's optimizing for a specific configuration. But by arriving at that configuration, it changes the environment that it's in. So it's no longer has access to what it was optimizing before because it changed. And that's something that the metagenes kind of uniquely enable, is the ability to keep track of what it has done over time, because it creates new metagenes based off of what it's doing right now. And so it's kind of gives it this temporal aspect where it can actively disrupt what it's optimizing for without losing track of what it's doing. And it's a little bit disappointing right now because in order for me to be able to stream and do this, have it running it live, it's I had to shrink down the number of neurons that I was using in the connections. But when I just sit here and let it run with, 500,000-600,000 neurons, you get some really, really interesting structures that come out of this. But right now it's kind of
that sounds awesome. Do you have like a screen grab of like what one of those larger structures looks like after some generations? I'm super curious.
I do. Just one second. One second. I'll pull up Discord real quick. I had just sent an image. That's the wrong one. I just sent an image of it to somebody else here just a little bit ago.
I'm also really fascinated to learn a little bit like what because you don't define the inputs and outputs of this spatially embedded network, but I'm really curious to see how that might come about. I guess like how that might come about when there's like a task involved. Oh, look at that. Oh, I see there's like this very linear spot like right there.
So yeah, sometimes it comes out with very, very organized. When I have a larger set of it, and this right here, this is 800 neurons. And so this structure, if you look at the other one with the nodes off, you can kind of see the organization behind it. But since it's a discretized system, there's several neurons here that are very close together.
It's fascinating that there's pairs and triplets there. That's really interesting.
And the visual aspect of it, this resembles like a typical neural network.
Interesting. But there's like no like this side is the input and that side is the output, right?
There is actually I do have distinct input and output neurons, and one of the things here you can see where it's defined number of input and number of output neurons. So there's 10 inputs and 20 outputs for the one we're working with right now. And so I was kind of struggling with how I was going to go about doing the input neurons and the output neurons and how they were going to be wired together. And so the only ones that have a backwards flow through the network are the output neurons. And so I wanted to make sure that it was always guaranteed that the output neurons were connected somewhere, because the last thing you want is to wire a network and have it not be able to get to the intended output. And so when an output neuron is finding its connectivity, it just has a sphere that increases until it hits another neuron. And I am still figuring out how to handle how the activation or what the signal is going to be coming through the neuron, because normally I'm using it based off the distance as far as how the signal degrades. But the input neurons are fixed in their location, but they also have what I call an interface neuron, which is a neuron where there's no change in the signal strength. It's basically like a feeler that can be put out for the neuron. And honestly, I'm not entirely sure about that. I think that's kind of a pointless concept, honestly, when I talk about it. But it has another neuron that it can basically move anywhere inside of the network to place the output. Or the input, I'm sorry.
Yeah, very interesting. Huh.
And that's a floating neuron.
Yeah. If it's movable, it's not really floating. It can be picked up and relocated.
Interesting. So if I can change direction here, Matthew, a little bit.
Yeah.
Certainly.
I'll stop the screen share and get back to the.
No problem. No problem. So one of the things that fascinates me is the notion of creating and finding a community of like-minded folk. And I know you and I have talked about this historically, particularly looking out to academia for that. I don't necessarily think academia is always the way to go for creating a community, but sometimes it helps. What's your own thinking currently associated with actually creating a community around this program?
So I am currently have a website called Public AI Playground, and it's kind of centered around Omega as a place for me to drop my research. My intent is to provide open access to what I'm working on, as well as give the opportunity for other people to upload their projects, or if they make use of my stuff, then they can post that on there and have their own place. I'm trying to work on getting that more developed, but again, I struggle with time a lot. And so right now I have just the basics of some of the mega documentation on there and some of the explanations for how things work. And as I go, I'm going to try and open that up to make it accessible to more people and make a kind of forum, or an, I guess you could say, an ad hoc community where people can go ahead and display their projects, or we can bring in more open source stuff like the language models that are being developed, that kind of stuff, just kind of as, you know, maybe not like a business platform like what you're seeing at a Hugging Face, but, you know, just a place where, you know, people can share their stuff.
Very good. Very good.
I love
Alyssa,
that.
any final thoughts, any final questions from Matt?
I love that. I think that having these communities that are not like within a university lab proper, right? But people who are just really interested in doing these sorts of things are so important, especially when there's people like you, Matt, who are like, I'm going to have this website, I'm going to put all my work up here, I'm going to have different ways that people can get involved and contribute. I love that. Like, I think that science really needs a lot more people like you, and people who are just really excited to create communities and to support others who are just really interested in this stuff. Because, you know, not everybody can go to a university, or maybe somebody is later on in their career and they see this kind of stuff and they want to get involved, you know, all sorts of reasons. So it's really exciting to see. I'm super enthusiastic about it.
Right. Well, and one of my big things is that, you know, not every great idea has come out of academia. You know, there's been people that have come clear out of left field with an idea, and it turns out to be something great. And AI, machine learning, artificial life in particular, has been something that I'm extremely passionate about. And I want to give people the opportunity to, one, see somebody actually doing their own independent research that might have applications, because I am 100% convinced of what I'm working on, at Mega in particular. Maybe not the spatial neural network. I mean, that might go nowhere, or it might turn out to be something really interesting. But the core algorithm itself, Mega, I think has uses in the real world. And I think that it's good for people to see a hobbyist actually striving to try and accomplish something like that. And I want it to be something that other people can have their own ideas about and interact with, and hopefully grow their own projects that might contribute.
Yay!
Very good, Matthew. So this is the section where I can talk about the stuff I've been working on. Let's take the idea of community, because this is my 28th year, 28 and a half years that I've been developing this stuff, all through the Ape SDK, as it's now called. And one of the things that interested me is there have been times where I've had a number of open source contributors, either formally through Apple and Intel, or informally through just people who are interested in partaking in some aspect of this simulation work. And it's always been really great to have people who are actively involved in the stuff that I'm doing. I've had a fellow called Bob Mottram who's worked on the simulation for maybe 5 years in a row, and then another 3-year stint. And just having that interaction with someone is really, you have this kind of gestalt thing where the sum of its parts are gradually greater in the interaction. So I'm not sure how it actually came about, like a lot of these ideas, but I was contacted by Dr. Liz Swan, and she asked me if I was interested in writing a follow-up chapter to my Origin of Mind chapter that I wrote in 2013. My Origin of Mind chapter is very interesting because it's probably the last academic paper. In fact, it is the last academic paper that I got out before I don't know how one would call it. Before professionally, it was more difficult for me to put out academic chapters, let's just say. So it represented a period of time just before contemporary machine learning had become relevant. So it was actually looking at a number of different simulation methods that achieved some form of AI at the end of it, fundamentally. And I love that chapter. It's a chapter that I did originally as a talk, and brought a lot of people together and got a lot of really great questions at the end of it. So being approached by Liz Swan for another chapter in the follow-up, which I think is called "Where is the Mind Now?" or something like that. The original one was called "Origins of Mind." Made me think that I needed to find a way of basically simulating what the contributors to my open source had been up until this point. And there have been many different contributors at many different levels, for want of a better term. Levels is not a particularly good term to use with regards to programming specifically, but they've had different agendas, different interests, and ultimately come to solve a different set of problems, each individually unique and amazing. So I started looking at generative AI as a means of creating these kind of contributions. And this is a very political thing, because obviously the notion of replacing software engineering with generative AI is still, being regularly discussed. And it is something where I've talked to a lot of my contemporaries that I work with and told them a little bit about what I'm trying to do. Many of them are very complimentary about the approach, but I think it kind of spells an interesting period of time when potentially, I'm not sure the number of open source projects. I think it's in the millions. I think it's in the order of 4 million, or maybe that's the number of podcasts there are. Anyway, there's some huge number of open source projects that exist. And the ability of having generative AI and maintaining these projects and actually adapting them and moving them forward as, as processes change, as operating systems change, as all these things change, strikes me as a very interesting result, basically, of generative AI. Now, somewhat politically, DeepSeek has become the new benchmark with regards to generative AI. It's also remarkably good at programming in C, which is the language that I write most of all my simulation in. So previously using the ChatGPT-based programming, 65% of it would compile. It was really a very rough shot associated with actually getting output. About 95 to 98% of DeepSeek C generated compiles. And it also, you can phrase very difficult, if you find bugs in software, you can describe the bugs to it and it will actually be able to trace the points that are causing the bugs quite successfully. So it's a very interesting project now, because I'm taking, so folks will be familiar from this channel associated with associated with London 1940, displayed at Copenhagen, where I was looking to get someone involved with this simulation work, because it was just getting too great. As Matthew has noted, I have young daughters. My time is relatively limited. My sleep capacity is relatively limited too. So these kind of things play a factor in it, but I'd love to get London 1940 back up and running. And there were half a dozen bugs, basically simple software bugs, relating primarily to the Apple version of the simulation, which I've been able to squash, irrespective of this generative AI discussion, although one of them was solved through generative AI. And that has reawakened me associated with this project. London 1940, for me, was a very exciting and very vibrant project. I think the movement between it being, well, it's a fascinating period of time, because it's a period of time where London was being bombed. If you remove the war from it, the war elements from it, then you get a far larger group of people that are interested in at least participating in the simulation. But there are other interesting examples, like, for example, the telephone directory is owned by, I think, Ancestry.com and British Telecom, an interesting, two entities to own. So you can't actually get there was a lawyer at this particular location, there was a doctor here, there was people making plates here, there was a, horseshoe maker at this particular location. You have to add that to the simulation after the fact. So the problems I was having with London 1940 related primarily to the amazing and eclectic number of building shapes that existed in London in 1940, and actually getting that back into the simulation, and then generating rooms within the buildings wasn't problematic to me, because I'd already written an internal room, based on tree structures, actually, to find, what rooms would optimize through various shaped buildings. But actually getting the building shapes as I needed them was the critical part. Now, through talking to the generative AI, I have a few ideas of how to solve this. There are a wide variety of solutions that already exist in Python, which is interesting as a C developer. So I tried to pull some of those out of Python into C, but I think there are simpler ways of actually framing the problem. And what becomes interesting now is my relationship to the project is very different than it was being a solo developer. I now literally have conversations with generative AI to create the components that I need. And what's interesting is this notion of shared source code where the paradigms remain the same, because the generative AI will love to create different paradigms at different places, and source code just comes together like spaghetti. But what you really want is you want to be able to comb the spaghetti into straight lines, ideally. And getting that kind of interaction is still something that I'm having issues with. I think it's just associated with how I actually frame it. But it is an interesting project. It's an interesting project from a documentation perspective as well. Now, how does all this relate to artificial life? This might be the big question. Once you have a simulation, I'm simulating Canterbury currently because it's the right size compared to London. Canterbury is about literally 100th the size of London. It's actually at the bottom of what the area of London that I'm going to be simulating. So simulating Canterbury will still be useful in the broader simulation, but it gives a very well-defined smaller area of which the buildings and the structures, obviously there's a famous cathedral in Canterbury, but there's a whole series of terrace houses around the cathedral. So simulating the internal structures of those is not so difficult. It's just actually getting the structures there. So that has been the past, I guess, 2 or 3 months that I've been working on this, with the view that once you have the structures there, you then have agent models that go through. They have professions, they have incomes, they have movement reasons, they have a wide variety of things that kind of take the simulation in various directions. And that is taking from my Ape SDK, what has historically been called Barbalet, what is now called Simulated Ape, taking those agent models and actually putting them in this case, Canterbury in 1940. I'm trying to generate as much reusable componentry. I have a friend who was big in video games and did a Las Vegas video game within the past decade. And he has a map of Las Vegas to a particular resolution. I think Las Vegas 1940 would be an interesting enough simulation too. So I don't think my obsession with regards to London and that area is really anything more than, at the time, we're talking about COVID here, through COVID, London had gotten, there was a strange series of both fictional books, but also really interesting, dissections of what happened to London in the late 30s to the late 40s, basically. Obviously, there's a war there, but in terms of architecture, in terms of a kind of cultural renaissance, a lot of that was being written about through COVID. And I think I found a number of like-minded folk, returning to my discussion with Matthew about this, that sometimes finding a community is a useful thing as well, just in terms of a motivator. So kind of juxtaposition of what used to be done by people who I'd communicate with, very similar in some regard to communicating with generative AI, but not quite as, just a different kind of communication. And seeing what they created through this, seeing now what the generative AI is creating through this. It's a very interesting and somewhat political project, which I'm really looking forward to actually finalizing into a chapter. I know I passed this one on to you, Dr. Adams, because she was looking for, emergent people in the field that might be able to write additional fascinating chapters. So your name was certainly pretty quickly in front of my head to get back to Liz. But anyway, that's the project as it is currently. Do either of you have any questions?
With generative AI, what's been your experience been? Do you use GPT at all?
No, that's what I'm saying. It's historically I used GPT to lead in, and I thought it was going to almost be a joke. I mean, I thought the whole notion of actually getting this to replace open source developers. Now, I have seen there are corners of GPT, which apparently have been expanded specifically around programming and specifically around, self-referencing programming and feedback associated with bugs and these kind of things. I wasn't ever able to get that out of ChatGPT. My view is ChatGPT is, as it's commercially available, is not particularly ideal to programming. I know there are spin-offs that claim to be programming for $12 a month and this kind of stuff. Part of open source is it's free as in free. I really didn't want to pay for anything, which is why DeepSeek coming along has just been fascinating. I've tried to run the local version. I think it's called Deep Code or CodeSeek or Code DeepSeek or whatever. Anyway, there's a code version as well, which has a smaller model. I've tried downloading it, tried using it. No, unfortunately, the web version is the way that I've been rolling recently, and it seems to actually provide what I need. The ability to describe bugs to it, specifically bugs that it has introduced, and it finalized that, usually a 2 or 3 iteration process. The difficulty with this is that whereas historically I would be programming and communicating and emailing, it's almost like it's like an introductory programmer. It's like working with someone who has a lot of great ideas but has never actually implemented them. So it's a very different thing, and it's very time consuming in one regard, but I think it's also quite fruitful in another regard, because it forces ideas. You can become very set in your ways when you develop open source for long periods of time. And it's forced me out of that to think, oh, it's actually changed this aspect of it, which makes this more interesting. These things will be able to fit together slightly better. I mean, you have to be on your A game still with the interaction. But yes, I have used ChatGPT historically, and it was going to be the end of this chapter if I had to actually do it. DeepSeek coming along has just been a complete saving grace to the whole thing and moved it into a different sphere.
I've played around a little bit with DeepSeek and the local models. I haven't had the opportunity to go too deep into it because this past month has been chaotic for me. But I'm looking forward to just kind of playing around with and seeing it, because if I could have a local model that I could run with my files and be able to actually, hold what I'm working on in context, that'd be game changing for me too.
Yeah, personally, I've actually been using generative AI models for all sorts of different things. I have tried it for programming, but to be honest, I kind of am still just in the groove of just like, I know how to do this, I'll just do it really quick, right? I think that I'm going to explore how new models can maybe make some of that faster. But outside of even programming, I've been using it for a lot, actually, like for studying concepts. So in my free time, I am always thinking like, oh, I really want to know, like, I took like thermodynamic courses in school, which was great, but I feel like I've forgotten all of it, right? And since this is known knowledge and there's a lot of data out there to train these models, I thought, well, you know what if I just have like do one of those like conversation sort of like chats with it. So I've been using the GPT, like the voice functionality, and you can like personalize your chatbot. And I've been having a blast. Like anytime I have about 30 minutes to just spare, I like to pull it up and it remembers the conversations before, and I will just go through things like, see what I did. A couple nights ago, I went through oh God, what was that proof? The incompleteness. What is the incompleteness? Yeah, Turing's incompleteness theorem. And I was really interested in learning like the mathematic structure for the proof, which I thought was really fun. So like I've been using it for things like that, which I really enjoy. But it's also really great for things like if you're writing some admin paperwork and you're like, rewrite this as a list, a bulleted list. Boop. Oh, okay, like turn this into a table. Boop. I love that. It can just do all that kind of stuff. So, I never really got the sense of like, oh, this is a tool that can write like my next novel for me. Like, no. Like it can do all sorts of things that are really unexpected. And I feel like I'm doing all of these experiments to sort of discover all the different ways that I can use it. But I really just see it as a tool and not something that can replace the general direction and the big projects that I'm working on. So yeah, I'm really looking forward to how these tools can speed up my own programming.
And as I'm putting this on YouTube, the hate can come directly to me, barbalet@gmail.com. But yeah, I think it's very funny. In particular, Sam Altman has featured in previous recordings, or in a previous recording at least. And I think what's fascinating is the impact that DeepSeek has had on the US economy in particular, because the speculation associated with AI in general has, been a source of great income and great, I see this on my LinkedIn frequently, that, you can see people quickly moving to their particular spheres with regards to this political thing that's come out, even to the point of banning it potentially. So I think it's a fascinating time for this. My hope is that my stuff can be orthogonal to this discussion and just say, this is a tool, let's use it to its best. But then let's use it against the, let's claim there are 4 million open source. Please, again, leave in the comments how many actual open source projects there are. Could be closer to 500,000. But the ability for these things to then come to what is an extremely rich and extremely well human created, again, copyright and other things might be a secondary element to this, is incredibly powerful. And I think it will impact humanity very much for the better. And rather than being just a means of kind of personally noble goals, I love it for moral philosophy as well. I like having discussions associated with the Second World War and what came out of the Second World War in terms of moral philosophy. But, there are other ways of using these things. But I think practically, in the realm of programming relating to the vast quantity of open source that already exists out there, I think it could be incredibly powerful. Now, GitHub, it's already come to some of this. Some of these large open source repositories have already come to some of this, but I don't think they're looking at it with the same kind of community pluralistic methods that I'm trying to instill in this. Now, I know there's generative rating papers currently about generative AI, and I know all these things. So I don't know what will happen to this paper. I always find my Origin of Mind paper is very rarely referenced and very rarely remembered, but I think of it actually relating to a lot of interesting stuff that comes out of this still. So putting my life in another academic paper, let's see what happens to that. But I would thoroughly recommend to Matt to actually get into the process of writing these things, because once you've done one, you lose all that sense of I'm a hobbyist, I'm not worthy, I'm not clean enough for academia. It becomes very much like, okay, I just have to do this process now in order to produce this thing. Whether or not it's read, whether or not it's taken away, that's secondary. But I think that just the personal endeavor of writing an academic paper about something that you've worked on that you clearly love in some fundamental sense is very important. And my first example of this was, I was one of 100 submissions where the remaining 99 were all academics. And I thought, oh no, there's no way I can get into this. Then 50, me and 49 academics. Then 25, me and 24 academics. And I realized very quickly that hobbyists actually have a really kind of novel and interesting way of looking at things, which isn't, it can be drawn out of academia in some regard, but I would thoroughly recommend you, publish your stuff and just get into the process of doing it. Because once you've done one, it's considerably less scary the second time you do it. And after you've done a few, then it's just like, okay, I know what I have to do here.
Right. And I intend on it. My struggle is that I have ADHD and I bounce around a lot. And so I find myself testing out new fitness functions, working on developing the core of Mega, which I'm getting surprisingly close to being satisfied to where I can go ahead and get my 1.0 release out, where I feel like I have everything where I want it to be. But I think my goal right now is going to be to get the real core features, the ideas that I have burning in my head out, and then to kind of present it as a whole instead of going and writing a paper about this part of it and then that part of it and then introducing things as I go. I would like to have the core components all the way developed and then be able to just say, hey, this is the algorithm, this is how it works, this is what I'm seeing coming out of it, without having to say, but I wish I could also do this. Because one thing that I'm looking at implementing next is breeding between metagenomes. So we can have like say we're working on different related problems with the same set of base genes. So we have the same material we're working with, but we're applying, let's say, we're working with chemistry, and we have something applied to drug discovery, and then you have another one discovered to or applied to material sciences. Being able to take the metagenomes that have developed out of those and breed those together to come up with something in between the spaces, and trying to see how that relates to basically selectively breeding instances of the algorithm, and seeing if we can come up with a way of being able to I guess share knowledge between and be able to direct it towards like selective breeding to make it more efficient at a given task. And those are things that I want to have built in, so that, you know, once I do write a paper about this, that it's easily extensible, where other people are interested, they can just hop in, read the documentation, and start building their own things. Because right now I can drop the code into, say, GPT and say, follow this template, write me a fitness function that does X, Y, and Z. And I can go from idea to a working fitness function for this in, you know, an hour or 2 hours. And then I can spend the rest of my time tweaking it, playing with it, and seeing what comes out. And I want to be able to be at a point where other people can do that too. And so that when I do talk about this, then somebody says, that's great, I think I know an application for this. I can just go sit down and, you know, go from start to finish relatively quickly and get to work on actually building the thing they're trying to build.
What's fascinating, I mean, having done the Biota podcast, was a period of time in Biota Live where we had biochemists, I think, connected with Lilly. I was contacted by a Pfizer chemist following as well, indicating that they were doing exactly what you're saying. They used, you know, very basic genetic algorithms to look at splicing drugs together and this kind of stuff. And it's fascinating because this whole field has gone on. I don't know how much they academically publish around this, but just to have an insight probably 15 years ago now into the fact that the drug companies were actually taking this stuff very seriously and utilizing it because it gives them an edge nominally. The commercial edge that they get out of this kind of stuff is really fascinating. So yeah, I think what you're saying is exactly true, that out of these things come, you know, a wealth of possibilities, basically.
Mm.
One of the other things that that I've applied this to is automatic programming. I've played around with evolving a multiplexer where you have the mapping of the outputs, and you're trying to evolve the program that represents how you get to those outputs. And I'm looking forward to exploring that further, and I think that that'd be particularly interesting working with the metagenome breeding, because you can start with the same, you know, programming tools and apply it to different problems. And you know, I'm hoping to be able to see more of an impact towards being able to, I guess, have a pre-constructed like programming language encoded inside of the metagenome, so that we can apply it to, you know, rapidly test new ideas and new solutions. And the whole point of the metagenome, or one of the points of the metagenome, is to, I guess, distribute effort, so that, you know, the effort you make to solve one problem can be also used to apply to a different problem, because you already have the hierarchy embedded into the encodings, and so the work's already preserved there, and we can pass it on to other instances and apply it without having to start from zero. And so I think that that is a way of offloading, and eventually I would like to try and explore genetic programming further to see just what's possible with this, because it's an entirely different way of going about doing genetic algorithms, and I really want to see how far it can go.
We can't wait to see as well.
Tom Ray's Tierra, bytecode, all this kind of stuff is worth studying in this light, because I think it'll show exactly what you're saying, that you can take almost a meta program and then see how the meta program evolves and then reference down. So I think you know, these are strong. Immediately I think of Tierra from that. It's not that everything's been done before, it's that things have been done in various areas in various different ways that are similar. But no, it's been a pleasure having the chance to chat with both of you. Thank you very, very much. I understand it's late where you both are, so I want to be respectful for your time in the evenings. But we need to do this again sometime. I'm looking forward to my conversation with Olaf, so if you see Olaf before I do, Dr. Adams, please let him know that I'm looking forward to having the chance to chat with him. And yeah, just expanding. If, you know Charles Offrey, right? He's not only a name but a person to you. So
of course, he's great.
He's absolutely fascinating. The idea that he started off a seed here that is then going to replicate into this video is something that excites me. Matt, always a pleasure having you on. Discord is the way to get in contact with all of us currently, but in particular with regards to your work. I no longer feel as what I'm not sure what the terminology is. I can't even remember the acronym of the board that got us all together. What is emergent artificial life? What's the what's the name of the book? It was the first conference before the main A-Life conference. It's late night where I am too.
ERA.
ERA.
ERA, yes, that's
ERA.
right.
So the ERA Discord channel is a good place to kind of get in contact with all of us. And certainly, Dr. Khan, I'm looking forward to hearing from you. I'd love for you to TikTokize all these videos, and please get in contact. Pleasure chatting with you both. Thank you very much for your evenings.
Yeah,
Awesome.
thank you.
Thank you so much. Love the conversation.
Okay.